Hello, everybody. My name is Mark Chupka. I'm the Vice President for Research and Programs here at the Energy Storage Association. Thank you for attending today's webinar on energy storage and essential environmental technology. This webinar is being recorded, and everyone who registered will also receive a link to the recording and slides within the next couple of days. Questions can be submitted at any time via the questions chat box in your browser, and we'll get to those after our speakers finish their presentations. In the text of your question, please indicate to whom you would like your question addressed. All meetings and teleconferences of the Energy Storage Association are held in accordance with our Antitrust Guidelines. We ask that you abide by these guidelines during today's webinar. The full guidelines are available in the members area of the ESA website. If you are not yet an ESA member and would like more information, you can reach out to my colleague, Brenda Lovell. Membership includes free access to all of our webinars, including many that are exclusively for members, among numerous other benefits. Please contact Brenda for more information. Before we begin, I would like to announce a couple of upcoming ESA events. The ESA Virtual Annual Conference will be held next week on April 21st and 22nd and is free to attend. Please check the ESA website for agenda and registration information. If you'd like to take a deep dive into storage planning, ESA is offering a seminar on June 16th through 17th. Check the ESA website for information, and we'll have registration available later this week. Today, we are exploring a very timely and newsworthy topic: the role of energy storage in improving environmental quality and reaching ambitious decarbonization goals. While renewable energy takes center stage in most of the conversation, energy storage is the deus ex machina that enables the desired outcomes of sustainability, reliability, and affordability. I'm delighted to introduce an excellent panel for today's discussion. First up will be Erin Childs, a senior manager at Strategy Consulting with years of experience in energy storage. She will describe the growing movement to replace aging fossil peaking plants in urban areas with energy storage, which maintains grid reliability while reducing local air pollution and promoting environmental justice. Gabe Cantor will be next. He is the Director of Plant Architecture and New Technology at Strata Clean Energy. Gabe will examine the role of storage in replacing peaking plants, as well as the broader issue of storage on the grid to integrate ever higher amounts of renewable generation. Our final presenter is Paul Denholm, who is the Principal Energy Analyst at the National Renewable Energy Laboratory. Paul was the primary author of an NREL analysis released a couple of weeks ago that looked at how Los Angeles could reach 100% renewable electricity supply in scenarios that featured energy storage as a cornerstone asset. After their remarks, we'll open up to audience Q&A. You can ask questions via the question chat box at any time, and we'll read those out for the presenters when we get to the Q&A session at the end. Now I'll turn it over to Erin.
Hello, everyone. My name is Erin Childs. As Mark mentioned, I'm a senior manager at Strategy Consulting, and I'll be talking today about some of the opportunities that we've seen for storage to advance the retirement of fossil fuel infrastructure, particularly in urban regions. To provide some brief background, Strategy Consulting is a globally connected, impact-driven firm on a mission to decarbonize energy systems. At Strategy, I focus on topics related to grid decarbonization, emerging technology, and sustainable business models, which means I get to work on some of the thorny structural issues that have the ability to really hamper or accelerate that transition. In keeping with that focus, we have been working with New York City community and environmental justice groups for about 2 years to develop a plan for how to advance clean community energy solutions in New York City. That work has included 3 main objectives. The first has really been crystallizing the costs that go along with the existing fossil fuel energy system. The second has been thinking about some technically feasible solutions that can help to reduce New York's dependence on fossil fuel infrastructure. And finally, we've been building alignment on that future state vision and working on a collaborative path forward. I'll be spending some of my time today focusing on this New York case study in particular, and then talking more broadly about the opportunities that we see for storage to address some of these urban environmental challenges. So the first thing that we had to do in this process was really to sharpen our understanding of why we still have peakers in urban areas and what role they play on the electrical system in this context. There's really three main reasons why peakers are currently such an important part of grid operations today. First, peakers have the ability to respond quickly to demand spikes in a way that other resources generally can't match. Second, peakers are relatively compact assets, so they're easier to site inside of urban areas. This is really important for providing in-area generation, which helps with both electrical stability and managing transmission constraints. Finally, peakers can provide a variety of reliability services that help to keep the lights on. The problem with this, of course, is that peakers tend to be disproportionately located in low-income communities of color. This map shows where peakers are located in New York and how that compares to some of the most vulnerable populations in the city. These peakers are not only a significant source of greenhouse gases, they also produce local pollutants like NOx, SOx, and criteria pollutants, all of which have some significant health impacts. SOx and NOx are known to cause damage near their emission sources and increase incidence of respiratory disease, cancer, and premature mortality. So this is where storage comes in. Storage is a must-have to replace the reliability services that peakers currently provide. Storage is well positioned to address some of the key challenges that we just talked about in terms of ramping capabilities, physical footprint, and other reliability services. The other thing that's really important to note about storage is it's not a far distant future kind of solution. This is something that we're seeing happening today. Storage is already being used as a solution that can replace urban peakers. In New York, LS Power has been leading the charge with its Ravenswood plant. In Southern California, SoCal Edison is moving forward with a portfolio of 4-hour batteries to address the retirement of the Puente Power Plant. And in the Bay Area, East Bay CCA is looking to do a combination of central station and distributed batteries. This is another great point I'd like to highlight, which is that storage has great flexibility to be used either as a utility scale or a distributed solution, which can help to address all of these challenges identified previously. Turning back to our New York case study, I do want to highlight that to fully replace peakers, we do need both renewables and storage. New York has plans to deploy significant offshore wind, rooftop solar, and energy efficiency, and we expect that storage will be crucial in integrating and balancing those resources. What you're seeing here is one of the most challenging weather days from 2030 in our analysis. We're seeing that offshore wind is really low, and we need storage to step up and ensure sufficient resource availability. So we're seeing that storage is in a great position to be charging from offshore wind, much of which is interconnected directly into the city. The great part about planning for both renewables and storage in this region is that the renewables are able to help charge the storage, which really helps to reduce transmission congestion, which can be a big challenge into this area. We do expect that New York's demand for storage will continue to grow, even as we are already seeing there's some pretty significant demand. As the state pursues some pretty strict zero emission, zero carbon goals, we are expecting to see that storage needs will be growing significantly. Our analysis was really focused on the years of 2025 and 2030, but as the state continues towards its goals in 2040, both renewables and storage will be an important part of the solution. The challenges that we've talked about and that we've been looking at in New York really are not unique to this region. These are challenges that are showing up across the country as cities are thinking about how to retire fossil assets, and community members are pushing the cities in that direction. The need for storage will continue to grow in all of these regions, and you can see here a sense of the magnitude of the challenge that we're facing. These are some huge numbers, right? We're looking at gigawatts of storage capacity across the country just to address these challenges. For folks who have found this discussion interesting, we'll be hosting a webinar with the Peak Coalition about our work in New York City next week, and we'd love to have your participation. Besides our work in New York, we're also turning back to the West Coast, specifically to look at the broader LA region. We're really hoping we can bring a similar lens to addressing peaker retirement in this area, helping folks to understand how storage can be a key tool to help enable the replacement and retirement of peakers in disadvantaged communities, and to continue this same approach of bringing together key stakeholders to develop collaborative solutions. With this, I will turn it over to you, Gabe.
All right, yeah, thank you so much. Yeah, and what I'm presenting today is actually gonna dovetail quite nicely with what Aaron just presented. My name is Gabe Cantor. I'm the Director of Plant Architecture and New Technology at Strata. I'm thrilled to be here today and to get the opportunity to talk about important big picture topics. I spend most of my day, day-to-day focusing on details of projects, optimizing layouts, specifying transformers, what have you. And it's really nice to be able to take a step back and remember why energy storage matters so much, kind of at the 30,000 foot level. So I'm going to give a brief intro to Strata, but I'm going to hang on. Yeah, there we go. I'm going to lead with this. Strata Solar, we're in the midst of a name change from Strata Solar to Strata Clean Energy. So that should give you an idea of kind of the direction that we're headed. We're a privately owned, vertically integrated developer, EPC, so we do engineering, procurement, construction, IPP, so we own and manage assets, generating assets, and we do O&M, we provide O&M services both for our own assets and for assets owned by others. And we've got about 400 people full-time, a relatively sizable solar and energy storage development pipeline. And about 3 years ago, we started the battery energy storage division, and that's really become a very key and important part of the company. And hence the name change from Strata Solar to Strata Clean Energy. And so today's topic is, how can energy storage help us go from where we are now to a future that's powered by renewables, and a future that's lower emission? So since time is pretty limited, I want to first look at why increasing renewables on the grid causes some challenges that requires more flexible and dispatchable resources, and then we'll look at a specific example. So this is the duck curve. If you haven't seen the duck curve before, welcome to the industry. This shows up in pretty much every presentation on energy storage and renewables, because it's such a great illustration of the challenge that happens when more and more solar comes online in the grid. So what this shows is the demand of a typical spring day in California, starting in 2012 with relatively low solar penetration, and then going throughout the years as more and more solar comes online. What happens is, instead of having a relatively smooth curve, as more solar comes online, you end up with a much steeper ramp rate towards the evening hours that requires more flexible and dispatchable resources to deal with. So Southern California Edison in 2013 was facing a challenge. They had the Mandalay Bay power plant, which was built in 1959, was retiring or was scheduled for retirement, and they needed a more flexible resource that would replace the capacity that they were going to be losing there and allow for increasing solar penetration. And so in 2013, they issued a RFP for capacity, and the Puente gas peaker power plant was awarded the contract. So that the Puente plant was proposed to be built right alongside the retiring power plant, and actually the retiring power plant was basically going to be abandoned in place. It was going to be a 262 megawatt simple cycle gas peaker, and it was going to be an improvement over the retiring Mandalay Bay power plant in every way. The problem was that the community didn't want it. Nobody wanted a power plant to be on their beach for the next 60 years. They wanted their beach back. And the community organized against it. They protested, and they were successful. The siting approval was denied for Puente, and the ISO, the grid operator, had issued a study indicating that storage could provide the reliability as an alternate. And so SCE, the utility, issued a solicitation for alternates instead of this Puente to provide the the needed reliability and capacity. And so from this solicitation in 2018, they awarded 7 different contracts totaling 195 megawatts of capacity. 6 of those were storage. 1 was demand response, not a gas peaker in sight there. And Strata, we won the largest proposal in that. And so that was kind of a turning point. And one of the wonderful things about this is that the capacity services that we offered were actually cheaper than what SCE had contracted for with the gas peaker. So it's a great success story here. And so just to look at the different attributes of energy storage compared to peakers and retiring plants, energy storage is superior in pretty much every way. It's got better ramp rates, better startup times, better ability to throttle. Peaker plants can only get turned down so low, whereas energy storage can basically operate from full charge to full discharge, so a 200% operating range. It's got no minimum run times, no startup costs, no local emissions, and the overall emission profile, and this is really important, the overall emission profile of energy storage declines over time as the grid gets cleaner, whereas peaker plants are, are constant. They burn fuel, and they're basically increasingly obsolete. They're obsolete when you build them, and they don't get better over time. And so, oh, and by the way, energy storage is a better investment. So this is one of the rare situations where investing for environmental reasons and investing for economic motivations will kind of lead you to the same place. So whether you're Gordon Gekko or the Lorax, investing in energy storage makes sense. And so this is Ventura Energy Storage. This is the plant that we built as a result of that SCE solicitation. It's going to be coming online later this month. It's as you can see, it's almost complete here, but this is 100 megawatts, 4 hours, so 100 megawatt hours of capacity. This is what resilience looks like on the grid. This is a peaker power, a peaker plant that is not subject to fuel risk. This is going to work whether the pipeline bursts or whether the coal stockpiles are frozen. This is a peaker plant with a fuel mix that's as diverse as the fuel mix of the grid at large. And this is a peaker plant that gets cleaner and cleaner over time as the grid decarbonizes. And we can look at so this is in California, serving the grid of greater LA, so one of the largest population centers in the United States. Across the country and on the opposite end of the size spectrum is this project here. So this is a small town, a small municipal utility in North Carolina, and we installed a battery project for them to shave their peaks. This project here provides peak capacity on winter mornings for heat on winter mornings with sunlight from the previous day. It'll provide air conditioning on summer afternoons with solar energy from the morning. So this is another example. Storage is here, it works, it's economic, and whether you're a small town or a big urban center, storage is possible. So we've talked about how storage can displace peakers, but let's look at what storage can actually do on the grid. Storage is an incredibly versatile asset. It can provide dispatchable real and reactive power. It can operate as it can emulate being a capacitor or an inductor or a generator or a load or any combination of those. And that capability is critical, and it allows it to provide to serve in a number of different applications. So I've put together a modest animation to drive home the point of how versatile storage is. It can be a load, it can be a generator, it's also a capacitor and inductor. Anything that's on the grid can be emulated by storage. So it can solve problems that it can do more than replace peakers. When you add storage to a conventional generator, it can make the generator operate more efficiently. You can have the storage provide the regulation function and smooth the output of the actual generator, and that can reduce thermal stresses. It can reduce the maintenance requirements, and it can make startup and shutdown more efficient. And when you add storage to renewables, it allows you to dispatch the energy whenever you need it. So you can control the ramp rate up and down, and you can time shift the energy, which makes it much more versatile. So that's those are yeah, that's what I've got for you today. Storage is winning against peakers today. It's future proof. Storage gets better over time as the grid decarbonizes. There's no local emissions. Storage is a good neighbor. It's you can locate it in places where locating a power plant would be difficult. You can locate it close to load. It's resilient. You won't have issues like like we saw in Texas last month with storage as peakers. And it's necessary. We need storage in order to continue on the path towards greater renewable penetration. So thank you. I'm going to hand it over to Paul at this point.
Thanks. That leads into kind of a specific study that we did here at the National Renewable Energy Lab, looking at the city of Los Angeles and the potential role of energy storage and opportunities to achieve the goals of achieving a 100% renewable, 100% clean power grid. So the LA 100 study was a result of an LA City Council motion that directed LADWP to evaluate a 100% renewable power grid. And this was a comprehensive study. I sometimes call it an IRP on steroids, looking at not only just kind of the traditional methods and approaches to looking at the power grid evolution, but also issues around the economic development and environmental justice. And this is something I think that's going to be increasingly we hear about, given the fact that a lot of these peaking plants are in urban centers, in EJ neighborhoods, and so I think energy storage, looking at energy storage in these areas is increasingly important. The LA 100 study looked at a lot of these different aspects, not just the power system, and this is kind of an overview. If you can download the entire study, and this kind of outlines the different chapter components. It looked at demand projections out to 2050. It looked at potential opportunities for customer adopted solar and storage, community impacts, but really the focus of what I'll be talking about today is the storage aspect of the bulk power system, as well as what happens on kind of the local network. So really, how much storage got built, what were the advantages of storage, why did storage get built, and what are the different types of storage, both kind of long duration and short duration. The scenario development looked at different pathways, ranging from SB 100, which is kind of the most conservative in terms of the pathways, allowing some use of natural gas, offsetting that with renewable energy credits, and achieving that by 2045, to some of the more aggressive scenarios that achieved 100% clean energy by 2035, and also restricted the use of natural gas, and also biofuels, grid-based combustion resources. So we had a range of scenarios. I won't go into the details. You can look at the report yourself to look at how these scenarios differ. But the important thing was to understand that this was a comprehensive analysis, not only of the power system, but also many different aspects of the power system, including resource adequacy and reliability under extreme weather scenarios. That was a really important part of this, making sure that the system would remain reliable under things like transmission outages from wildfires, and quite frankly, some of the restrictions that resulted in going with a kind of traditional, I don't want to call it short duration storage, but kind of non-seasonal storage option. The key elements around making sure that you've got enough in-basin resources so that when the transmission lines go out, you can maintain reliability and operational reliability and resource adequacy. So there's a bunch of different simulations that we did of different weather years under different impacts, complete distribution system modeling to make sure you could handle all the distributed resources. So kind of advancing the state of the art and the modeling capabilities to really kind of reveal some of these issues around whether or not storage and what role storage could play. We modeled essentially two types of storage. Your diurnal storage, and we always struggle with what to call this, long, short, medium, it doesn't really matter. Diurnal storage is something 10 hours or less. So this is really your batteries, your pump storage. And then seasonal storage being the longer duration, weekly, monthly issues around extreme events, transmission outages, the classic issues of getting too much wind and solar during the spring, not enough during the late summer and into the fall. So those are the kind of two different types of storage technologies modeled. And across all the scenarios, we do see significant deployment. So these are the results of the current mix in LA. This is the capacity mix, not an energy mix. This is what LADWP has right now in the left. And then moving to the right columns, you see the mixes in 2045. So the things to pay attention to if you're interested in storage are the pinkish colors represent, these are your battery storage, whether or not it's deployed behind the meter, and the lighter color, the utility battery storage, the existing pumped hydro at the Castaic plant, and then also not explicitly broken out here in terms of the megawatts of battery component, but a large amount of PV plus batteries. So that maybe the darker orange being the plants that were developed with batteries. So in total, a large amount of battery capacity in addition to the existing pump storage. And then on top of that, long duration storage in the form of combustion turbines burning hydrogen or other renewably derived fuels. So these would be essentially making hydrogen in the off-peak season, spring, storing that in the underground formations or other large formations, and then using that resource in the summer to offset the decrease in renewable resources. So those are kind of the two classes of resources built. And when we go to the annual generation, you can see that the amount that goes through storage isn't that great. And this is one of the important things about storage is, the capacity factors of storage plants are typically fairly low. They're really around reliability. I mean, this goes back to the argument about peaking plants. Peaking plants inherently have low capacity factors, and that's fine. That's the way the power system needs them to operate. So it's not necessarily about the energy throughput. It's making sure that capacity is available when it's needed. So the actual amount of energy that's cycled through storage may be relatively small, but it's still super important in terms of providing those reliability services. In these cases, it's a little bit easier to see. And the below the zero, that's the energy that was actually used in the storage process. So that's the energy that was either stored in those batteries, pumped storage, or used to make hydrogen. So again, the amount of energy less important than the capacity availability. And this is the chart that really shows the role of seasonal storage. You can see here when we're making that hydrogen, in this case, in the spring, and then using it later in the fall and late summer. There were some particularly challenging times in November. In some of the weather years we analyzed, where there just wasn't very much wind and solar available on some of these days. And short duration storage helps, but it's really the seasonal storage that helps you maintain that operational reliability. And you can see that we get usage of storage during all the periods of time, the diurnal storage, but it's the seasonal storage that's kind of the most obvious thing in terms of helping maintain that reliability during the challenging periods. Again, all of this is focused around 100%. This isn't saying that you need seasonal storage now. This is when you get into these deep decarbonization scenarios. That's when this becomes more important. So the bottom line, in terms of how much storage got built across all scenarios, we always built by 2045 at least 2,700 megawatts of this diurnal storage. This is the new diurnal storage built, and mostly in the form of batteries between 4 and 8 hours in duration. Some of that's coupled with storage, or some of that's coupled with solar. A lot of it is standalone. But the point is that across all scenarios, in a system that right now peaks around 6,000 megawatts and may peak as high as 10,000 megawatts in the future, with the additional electric vehicle loads, this is a large fraction of the resources. But we can't just do it with diurnal storage. We do need some firm in-basin resources. There's simply not enough transmission going into the LA Basin, so we do rely on some, in this case, RE-fueled combustion turbines fueled by a renewably derived fuel. These have extremely low capacity factors. They're really there for reliability purposes in terms of if the transmission line goes down or you get extreme weather. They have lower capacity factors than even kind of, in many cases, even a current peaking capacity. This wasn't a one-to-one replacement, but we did replace a substantial fraction of the in-basin capacity. So it would have been great if we could have just done this all with diurnal storage and not have any of these thermal resources. But again, to deal with the extreme events is why we relied on those. But again, the bulk of the work on a day-to-day basis is operating the diurnal storage battery plants and getting to what Gabe was talking about in terms of providing local voltage support, basically allowing the existing thermal plants to be shut down for provision of those reliability services. And that's really important because even though they're still there, we want to avoid their use for providing things like what's traditionally called reliability must run. supporting the transmission network. We can do all that with the batteries and the in-basin resources, and really only run these combustion resources when they're absolutely needed for energy purposes. So the full report's available. We've got it's over 1,000 pages. There's also an executive summary, and there's also a data viewer online available where you can kind of go through the different scenarios, look at the builds, look at the results, and some of the other results. And with that, I'm happy to turn it over to our leader here and participate in any questions.
Thanks so much, Paul, and to all the panelists. Those were just outstanding presentations, and we've already got some questions piling up in the chat box. But thank you for the folks who have already submitted, but you can continue to ask questions during the remainder of this webinar, and we'll try to get to as many of those as we can. It's tough to figure out where to start, but here's a question having to do with potential downsides. This is for Aaron. Has Strategen looked at the impacts on the local urban communities from a job loss perspective from the retirement of peakers? Similar to coal plant retirements in rural areas, there are negative socioeconomic impacts in local areas from peaker retirements that should be considered as part of the big picture.
Yeah, that's a great question. I mean, and as you can imagine, given that we're working with members of those communities, they are particularly interested in those questions. Those get pretty close to home. So, it's certainly a balance, right? I think this is part of why the community groups that we're working with are looking very heavily at resources that can be located in New York City, whether that's offshore wind, whether that's storage, right? They do want solutions that are not only cleaning the energy systems, but are giving back to the community more broadly.
Okay, thank you. Here's one that any of you, I think, might be able to address. Can someone comment on the fact that energy storage is a limited energy resource? And how can resource owners justify the high initial cost compared to the relatively low revenues from the wholesale energy market for grid support resources?
So I can take a stab at that one, but then certainly would be interested to hear from everyone else, especially Gabe. But when we looked at energy storage in New York, it was actually more cost effective than peakers. Just thinking about, capacity revenues, energy market revenues, et cetera. And that doesn't even factor in the benefits, the incremental benefits that we see from cost of emission reduction. We were looking at close to $300 million a year in terms of pollutant costs. So, that's another factor I think that oftentimes doesn't get included in the strict kind of cost benefit energy revenue calculations.
Yeah, I can add to that a little bit. So it's true that energy storage is duration limited, but the applications that we're using it for, the durations are adequate. So if you're looking at sort of the duck curve, right, a 4-hour resource actually fits pretty well with the length of the peak and the kind of length of the amount of time that you have kind of overproduction in the belly of the duck. So that slots in pretty well with the use case of replacing peakers. And in terms of revenue, at least for the Ventura project that I showed, that has some revenue that's contracted with SCE and some that's merchant as well, and the amount of volatility in the wholesale price is enough for us to justify that project, and the investment's pretty good.
Yeah, just to follow up on that, the capacity factor of a typical peaker is going to be, often less than 10%. So you're not making your money on the energy market anyway. You're making your money through capacity markets or through scarcity pricing. And in many cases, energy storage will have equal or greater capacity factors because it will provide not only peaking services, but it'll also be serving, it'll also be providing load leveling during non-peaking season. So we've seen, storage plants with higher capacity factors than peaking resources.
All right, thanks. Those are very responsive. Here's a question for Paul from a colleague at another national lab. Were the hydrogen resources in the LA 100 study selected on a least cost basis? Were new pumped hydro facilities a resource option?
We had a limited selection of new pump storage resources available to us. In some cases, the model chose them. In other cases, it didn't. The need for hydrogen was essentially the need for extremely long duration. So pump storage couldn't provide the in-basin capacity needs. We needed something in-basin that could run for 3 weeks at a time, especially during transmission outages. So pumped storage couldn't provide the services needed in-basin.
I have a follow-up question for Paul. How much do electricity rates go up in your scenarios?
So again, one thing to keep in mind that their base case was SB 100, which is essentially 100% clean energy based on sales, and so that's your baseline. So the increases associated with the other cases weren't that great, with the exception of the early no biofuels. The aggressive decarbonization by 2035 was a fair amount more expensive in those cases because of the need to deploy some of these relatively immature technologies a little bit earlier and restrictions on the fuel mix. But the cases that we had a little bit more fuel flexibility compared to something like SB 100, the increases were quite modest.
Okay, thanks. I'm thinking that this might best be posed to Gabe, although I think anybody can chime in. The question is, what is the impact of the proposed Biden investment tax credit for standalone storage? Can the supply chain handle it?
We are anticipating a surge in demand. It's interesting. So I've been with in kind of the renewables industry for a while now, and I was there kind of when utility scale solar kind of hit that inflection point and demand skyrocketed. And I think we're in for something similar on storage, if not even more dramatic. The tax credit certainly helps, and the fact that the proposed tax credit is refundable is a really good thing, and it means that whether you have the tax liability or not, that benefit is going to be available to you.
Okay, I'm going to pose this one to Aaron. How are the storage facilities being reviewed in the community? How is the transition for stranded assets being managed? And I'm going to add a question about, are there concerns about safety of storage in dense urban areas?
Yeah, good questions all around. Maybe I'll speak to the safety question first. We do a good amount of work with the California Energy Storage Alliance. And I know they have been spending a lot of time thinking about that safety question, although I expect that Gabe will have much more detailed insights than I can provide on that. The question of the transition and stranded assets is a really good one. I mean, I think community members recognize that this is a transition. This is not something that's going to happen overnight. We need to figure out how to make it happen, and they are happy to work with utilities and whoever is going to be impacted by this. But there is also a sense of urgency. I mean, this is in their backyard. I think COVID has really hammered home the fact that there are times where the air quality and the health impacts, particularly to those communities who are host to fossil assets, is particularly painful. And so I think, recognizing that this needs to be done in a smart and informed way, there's also a sense of urgency and impatience to get started.
Okay, thank you. So some technical questions, sort of battery technology questions for Gabe. One, I think, is responding to some of the diagrams you had. Batteries, particularly lithium ion, cannot be fully discharged or charged 100% without a decrease in life. What battery technology are you using?
The systems that we have deployed so far are various flavors of lithium ion chemistry, LFP and NMC and NCA. It's true that they do degrade over time, and we handle that with a combination of initial oversizing and a plan to add capacity over time as the batteries degrade. So that's sort of baked into the facility's design and the operation plan.
Yeah, I think one thing I would just add, just an observation that ramping potential from negative 100% to positive 100% can be a very handy thing to have, but you won't necessarily be using it every single cycle across that range. So I think that's one way to manage expected lifetime. Speaking of expected lifetime, here's a question about how can batteries be used or recycled at the end of their lifetime?
That's a great question, and it's something that's being worked on, but I don't think the answers are all that satisfying just yet. The recycling infrastructure is being built, but it doesn't exist just yet. But generally speaking, the cobalt-rich lithium-ion chemistries, there's a lot of value in the raw materials in the batteries, so it's going to be economically advantageous to recycle those and those materials and use them to create new batteries. Our suppliers have committed to us to recycle the batteries if at the end of life, provided that we ship them to a recycling facility. And so that's kind of baked into our decommissioning plans for projects.
Okay, thanks. I'm gonna turn back to Paul. It's an interesting question here. What's the timeline for incorporating hydrogen combustion into the mix, considering effective NOx emission controls technologies do not currently exist?
So most of the turbine manufacturers have announced that they're moving to increased hydrogen blend. So most of them will say that you can burn up to X amount of hydrogen. Always have to be a little bit careful because they typically quote that on a volumetric basis, not on an energy basis, which is a little annoying. But yeah, so starting off with hydrogen blends up to 30% in the next few years. LADVP is pushing towards hydrogen combustion at a combined cycle plant in Utah to replace the coal plant that's there. And then just kind of watching the development. I'm not a mechanical engineer. I don't really understand all the aspects of what's needed in emission control and burn modifications. But most of the turbine manufacturers, particularly those out of Europe, are really pushing hard on developing the technology to get up to 100% hydrogen combustion. But beyond that, you kind of have to talk to the vendors.
Okay, that's getting through a few more related questions. There's an observation, I think, maybe for for any of you. A 4-hour battery energy storage system will actually last longer than 4 hours if it follows PV output in late afternoon. The output would be blended. I think that it's the point that 4 hours is at maximum output levels, and smaller output levels would last a little bit longer. Anybody want to make a comment on that? A piece of sort of technology?
You know, I might chime in here and say that part of how we've been thinking about it is around stored energy capability. So, you know, how many megawatt hours or gigawatt hours of stored energy do you need to ride out a weather variation or a peak in demand? And when you think about your peak capacity output needs and your stored energy capability, that gives you kind of an implied duration. But that is a very good point, right? We're not necessarily implying that a 4-hour solution or an 8-hour solution needs to be dispatching at full capacity for all, 4 or 8 of those hours. It's really to help kind of understand what the grid needs in order to be reliable.
Yeah, I think a useful metaphor to think about energy storage is think of a water tank. The amount of energy stored is the amount of water in that tank, and then the discharge rate would be kind of the size of the valve to drain that tank. So you can open up the valve all the way and it'll drain in 4 hours, or you can modulate that valve and open up part of the way. That same amount of water would take a lot longer than 4 hours to drain. So yeah, it's a good point.
Yeah, I think it's an excellent way to think about it. This is addressed to Gabe, but I think others might have a point of view on this question. The U.S. is preparing to invest heavily in infrastructure and also supply chains. Are you seeing customers ask for domestically produced batteries? And does this pose a problem for lithium?
We have not seen customers demand domestically produced batteries so far. There aren't that many choices for domestically produced batteries in the stationary energy storage space. That would pretty much leave you with Tesla. I'm hopeful that there's going to be more battery manufacturing capacity added domestically in the future.
I will maybe chime in on this and just say that I think as we look out the next 10, 20 years, we are seeing a really substantial growth in need for energy storage solutions. So I think regardless of where those solutions come from, there is need to grow the supply chain and ensure that folks like Gabe are in a good position to help get the systems built and bring them online in a timely fashion.
All right. So it was a compound question that also had end of life considerations, but the first part of the question was not posed earlier. So what is the typical life of batteries used in utility scale storage? And I'll just add, and do we see that those lifetimes getting longer, which actually has some supply chain implications as well?
The lifetime of the batteries is, you can think of it as sort of 2 components. There's cycle life and calendar life. we are seeing guarantees for batteries, for battery cells going out to 25 years from some of the major battery suppliers, 25 years and about 12,000 cycles. And that's not until the battery kind of stops working. That's until the capacity fades to about 60% of the initial capacity. But it depends on the chemistry and the application and the duty cycle. So a shorter duration frequency regulation battery will probably not last as long as like a 4-hour battery that's cycling a few hundred times a year.
What's your impression? The rate of improvement in either cycle life or calendar life over the last, say, 5 to 10 years?
It's been pretty dramatic. A few years ago, it was hard to find batteries with guarantees over 10 years. And so now CATL, one of the major battery manufacturers, is offering guarantees out to 25 years. So that's pretty amazing. Yeah, the cycle lives were in the low thousands, and now they're tens of thousands of cycles to end of life. So that it's lithium-ion technology has been improving pretty quickly.
Yeah, I'm going to have this will be the final question, and I think I can direct it to all of you. Do you think the upfront cost of energy storage will continue to go down further in the next few years, or have we flatlined for a bit? So any of you can answer, and Paul, certainly perhaps the assumptions in the LA 100 study regarding storage costs might be relevant here.
Yes, we're not done yet. We have a long ways to go for lithium technologies.
Anyone else?
I expect that the prices are going to continue to trend downwards. I don't think it's going to be a kind of smooth trend. There's going to be some some noise in that forward pricing curve, so to speak. But yeah, one of the issues with stationary storage applications is that it seems to take a back seat, from the battery cell manufacturer's perspective to EVs. It seems like the EV market might be more profitable for them, and so we kind of see ripple effects to changes in the EV market on the storage side in terms of pricing and availability. But generally, I think manufacturing capacity for batteries is going to increase over time, and prices will trend down.
Agreed with both Gabe and Paul. I think something we're really excited to see specifically is seeing some longer duration solutions becoming cost competitive, especially as we talk about some of these really deep decarbonization scenarios, zero carbon grids like what Paul was talking about. That's going to be, I think, a really big piece of the overall solution.
Well, thank you. I'm afraid we've arrived at the end of the hour, and I'd like to thank the presenters for a very interesting and informative session. Before we conclude, I'd like to remind you to register for the ESA Energy Storage Virtual Conference on April 21st, 22nd, and to take a look at the planning seminar on June 16th and 17th. Please stay safe and healthy, and have a great rest of the day.